Here's a very quick overview of the central limit theorem. Central limit theorem has three main parts. The first is repetitive sampling will produce sample means that have a mean equal to the population mean. The second part says that repetitive sampling will produce a standard deviation of sample means that's equal to the standard deviation of the population over the square root of n. And then the third and most important probably for us is the fact that you can take a distribution that you don't know is normally distributed and use normal techniques, normal curve techniques on the sample means. And this little applet here at the onlinestatbook.com can demonstrate this. So here's a population that's 0 through 32. So you could think of these as individual ping pong balls perhaps in a hat. If you took all 32 of them, they have a mean of 16, which makes sense, and a standard deviation of population of 9.52. What a lot of people get the misconception of is that this changes as you sample. The population doesn't change at all. So when I take a look at sampling a sample size of 10 balls at a time, here's 10 samples repetitively done. And that is with replacement. So you pick a ping pong ball, you put it back, right? The sample mean of those 10 is here. If you do that again, if I do that 10 at a time, 5 times, you can see those blue sample means, blue sample means, blue sample means. And what you see is the middle becomes very populated, the middle, and the tails become weak. And if I do that 10,000 times, we get something that looks approximately normally distributed. So the population did not change at all. It's the sample means that are normally distributed. And then you can check the characteristics of the central limit theorem. The mean of sample means is 15.94. 16 is the population. So theoretically, if I continue to sample, this will get to 16, but very close already. The standard deviation of the population was 9.52. If you take 9.52, which remember the standard deviation of the sample means called the standard error, if you look at that 9.52 over the square root of 10, 9.52 square root of 10 is something just a little bigger than 3. You're going to get something in the neighborhood of 3 and a little bit of change, right? We could grab a calculator and get this, but we don't need to, because I can show you here that that standard deviation is right there at 2.98. That's the standard deviation of these sample means. And then the third part, you can see that the sample means are normally distributed even though the population was not. So that's a little overview of the central limit theorem from a uniform distribution. I could also make a distribution just to show you how powerful this theorem really is that has a really big gap in the middle of the distribution, so bimodal. But I could sample 10 at a time again. And again, if you read carefully, we like 30 or more to have an approximately normally distributed sample means. So if I took 25 5 times and 25 5 times and I kept getting the sample mean, notice how the middle fills up. And in the end, here comes that normal approximation again. Means, very similar, 10.38 divided by the square root of 25. So 10.38 divided by 5 will get you a number just a little over 2, and you see that here. So hopefully this helps with a quick overview of the central limit theorem.